Hello, thank you for joining. My name is Alex, and today I will talk about the satellite data and how we use serverless workflows for it. Uh, the company I'm working for, uh, they're doing space. They're doing. Is it better? Okay, so they're doing spacecraft and satellite missions, and my role is like once the data is downlinked, how to distribute it towards the companies. And also because of the aerospace field, we are regulated, we have certain requirements we need to obey, and it's easy and more straightforward way to do it with public cloud providers like Amazon. And today I will cover the typical workflows, the typical challenges we have, and how to address them. And also I will show the open source data sets that can be used by the engineers to build exciting things and analyze the man-made activity, implement analytical workflows, and just enriching the corporate data sets with a public large data set. And I will start with an overview of what is the satellite data. So the current satellites are powerful tools to monitor the Earth from orbit, and given this, even up to getting the daily data set, it's possible to see how the world is changing and how the man-made activity is visible and how the living resources are changing. And there's a consistent data set which can be analyzed as a time series of different layers. So the current satellites allow monitoring up to daily with open source and commercial but not that expensive missions in a moderate resolution. So by moderate, they usually mean from 10 to 30 meters. So this in 1 pixel. So this resolution doesn't allow to see a car or a man, but it allows to see a growing field, a road, a pipeline, a building, and since the data is delivered every day, not like once a year or a couple times a year, it is possible to observe to create time series and understand how the world is changing. So again, it's for different types of satellites, for multispectral, radar, hyperspectral, laser. They allow to create different layers for the satellite data, and for every point in the Earth, observe them like separate layers at a global scale and to compare. So these observations are consistent. The imagery is taken in the same time of day between 11 a.m. and 12 a.m. To compare these data sets from different years. And the archive is pretty deep, so they started consistent monitoring missions back in the 40 years ago in 70s. So it's really possible to see not only the changes which happened over the last week, but also the changes that happened over the many years. And the sensors, they especially for the multispectral, they're tuned specifically to seeing different features in the growing, in emissions, in different types of activities. And having these layers, it's possible to create what they call data cubes, but generally it's like a time series of different types of data which observe the same phenomena, and altogether it's possible to train models with ML and AI, and sometimes even equations is enough for simpler simpler tasks to understand so what is changing, sometimes even to predict yield, predict man-made activity, with just the satellite data, with no or very small of the ground truth data, which is really interesting for remote regions or for the regions where there is not so good communication and so good scouting there. I have a number of examples of real projects that currently proven they work. Sometimes they're commercial projects. So for example, this is a company called One Soil. What they did is that they trained the model to understand the crop at the global scale. So there's an example of US, but feel free to check them out because they have a global map. And on the field level, in up to 30 meters in 1 pixel, they know what's growing there, and they can predict yield and predict the development for the current year, starting even I think in June or maybe early in July, generally before any type of predictions are there. Um, So if we zoom in, you can see that at the field level, and for every pixel, they understand what crop is going there. They see the field productivity of the green mass, and they can expect that by seeing how the green mass is developed, how good the yield is gonna be. Yeah, it's online, it's publicly available, so feel free to check it out. Another typical project is the building detection. So building detection, it's really interesting how it's done in moderate resolution data when you have only 10 meters on your pixel. So generally what they do is they compare the time series and see what is changing. And what is changing is usually the vegetation or the trees. So everything which is not changing is probably other buildings. So the best way is really to subtract the activity and what is rest is the buildings, and for a certain spectrum it's really visible that this is concrete, this is metal, and it's possible to adjust the current maps of buildings like OpenStreetMap with current data. Another typical application is the scene pipelines, the thermal effects observed with the satellites, even with a less resolution, but very different from what's on the background, help to understand so where is the pipeline, how it can be, how active it is, where it's going, and it's very interesting to observe, especially the China is like one of the very interesting targets in this case because US don't have much of the other data sources where they can see the activity, and this one is objective, is easy to do, and fast to deliver. All these types of applications can be done on the open source data from the government satellite missions, and Landsat, like the mission started in the 70s with the most recent called Landsat 8, is a really like a gold standard of the satellite data for observations. They provide 11 they provide 9 spectral bands, and from green, blue, red, near infrared, thermal bands, all this data is possible to see every 16 days of what is going and what is changing, though the resolution of 30 to 100 meters is not always the best, but it's really very consistent. The more modern satellite called Sentinel-2 is the European Space Mission satellite mission, and it provides up to 5 days with 2 satellites of 12 multispectral bands, really bright, vivid data. But the thing is that they have not that deep archive, so it's only like 3 or 4 years for some locations. In addition to multispectral data, there's also the radar data when they just collect the radio response from the surface, which allows to see not the like visible pixels, but the reflection, like elevations, like buildings of ships. For example, for maritime applications, it's really visible how the metal ships reflect brighter than the surface of the ocean. So all this data is overall, by now, it's 8 petabytes of the publicly available data, which is available on Amazon Web Services and Google Cloud storages, both available for free or almost for free for all the engineers in the world to build their ML models and use it for their purposes. But there are a certain number of challenges. And the image set is primarily the most challenging one. So for example, one radar picture takes about 1 gigabyte, and not every computer can easily process it. Another issue is that even you have this large picture, it's like 200 by 200 kilometers, and your target area of interest is way less, and you don't need to process all this like a gigabyte per picture when you need a couple of hundreds of them every time. So you want to read specifically your area of interest. Another thing is the for the data sets and the latency, and this is more like a challenge for people who want to adjust to do the faster predictions. So for example, the image is available at 11 a.m. in the morning, and you need to use this data by 1 p.m. for the predictions. So you need to process really fast and make sure that it's consistent with other data sets. So it's really the issue of the time and availability is there. Another thing is the interoperability. Though every mission tries to be consistent with each other, but for example, Landsat and Sentinel, they require a certain cross-calibration, which is not a straightforward task because they have slightly different types of multispectral sensors. Another thing is that the satellites, they observe Earth over the atmosphere, and when the light particle comes 2 times back and forth through the atmosphere, it loses a significant number of signal depending on the location. So it's really important to predict how much of the light was absorbed by the atmosphere and adjust to this number. So this is primarily the challenge for the interoperability and harmonization. And one thing we see like a company that distributes the satellite data is that the availability, the demand is very unstable. So for the agricultural seasons, we have high peaks. For the day when we do an acquisition, we have high peaks. And depending on the clients and the integration projects, we need to make sure that our system is capable to deliver and be resistant to these peak loads. To example how we address these satellite these challenges, let me show the typical workflow for the preparing the data from these raw, huge data sets available on Amazon and GCP to what is the time series of features. So generally, we read the large images and as their original size. Then we need to do the co-registration, do a little bit of the adjustment of the position because they sometimes a little bit offset, and we need to make sure that they're radiometrically consistent. After that, we are ready to read the area of interest we need. Once we read these areas, it's possible to extract features because they are already consistent. So once we do the feature extraction, it's really possible to create a time series of them, and these like features like high values, low values, medians, whatever, can be fed to the ML and AI workflows. Oops. Initially, we tried to do this on the in-house computers, and this is a picture now from not our computers because we like a 20 people startup, but this is pictures from the NASA data centers for every year, from many different years. But for both of us, the challenge is the same because of the peak loads and really large data sets, and that from this data set we need less than 1%. It's not feasible to do it on the instances. And for us, it was like a pretty interesting project how we switched all our processing primarily to the serverless, except for the just the watchdog operations, because from the first month we saw our checks from the before when we moved from EC2 to Lambda functions, we saw that our expenses cut by 4. So for us, serverless helped a lot. And by serverless, I generally mean the Lambda functions we actually use in our purposes. Another good option could be the Google functions, both of them because they can be deployed in the same data center where the satellite data is to save the traffic on the sending the data back and forth. So the serverless is on demand, it's scalable, so once we reach to the limit of the 40,000 instances of Lambda functions working at a time, but generally this is what we need, not more than that of processing. And let me give you 3 examples of the operations we did specifically with Lambda function and how they help. So the first one is how can we access the needed part of the image, not the whole picture. So in mapping, it's called tiling, when all the image is clipped by the little square tiles of 256 by 256 pixels, and at different zoom levels this number of tiles is different, and you can view deeper and deeper to the 1 pixel level. And all the pixels are addressed, and with data sources like S3, it's possible not to read the whole picture, but to read specifically pixels in a range. And having an ability to make this window read of the pixels, it's possible to make an API that asks for specifically this couple of tiles. And since this operation is less than 3 seconds, for us it was a straightforward way to make a Lambda function for every API call and do an API gateway to deliver the clipped tiles to the user instead of sending the whole picture. And just connecting of the 3 services of the S3 through Lambda function and to the API gateway was a straightforward way to make a tile server to deliver a needed part of every image to the user in the matter of 3 seconds. Another problem we are doing, even in a very simple workflows, is the processing is different from the parameters. So for example, cloud images need one type of the radiometric correction. Cloudless images require different types of cloud corrections, or from the location, or from any other parameters. It can be not a very difficult tree, but it's really easy to abstract some of the parts of the process into larger blocks and organize them into higher level steps, because, for example, cloudless images, they require less steps of processing, and cloudy require not only other parameters but also other additional blocks. So the logical way for us to organize it was the step functions and the lambda functions, primarily because they have the same entry point, and depending on the parameters and the outputs, you can make additional blocks if for certain images they are required. And the most challenging part we saw for the processing was how we need to address the large amount of data. And if you're talking about 7 to 8 of petabytes of the public domain data, and for which means that for every location in the world, like for San Jose, it is 2,000 observations available, and we need to see how these observations were changing over all these times. And even we subtract all the cloud images and we have 50 relevant features, it means like a pretty significant processing that doesn't fit a lambda function. So we'll have to use something more expensive. And to address that, the logical thing for us was to have the step functions, but to connect them with batch processing, because we couldn't be sure that every function and every step of the processing could be less than 5 minutes, less than 5 minutes. So we had to use AWS batch, and though it was a pretty expensive type of processing, we realized that it's possible to use spot instances, because for some of these workflows, the very fast and very immediate response was not required. So we switched to spot, and it also was a significant save of the resources for us. And primarily this was all I wanted to show about the satellite imagery. And like my main takeaways here is that there is a very rich data set available publicly for ML workflows, for AI workflows, and every time when people are really fighting for the data, please keep in mind that there is an objective global data set that can be used, and it may be very, very helpful to check it out, see the signals, and realize that probably your answer is there and you don't have to build your own pretty expensive infrastructure. Also, the second takeaway is that the serverless is the cheapest and easiest approach, because first of all, it's faster to deploy, especially for the experiments and the first scene of the maybe some correlations. And secondly, because you can only read what you need. And like I saw that many of the projects we did was done by just one developer or a small team, or like during a hackathon or over a weekend. So it really means that having a remote sensing unit in your project doesn't require like a huge team of people. It can be just started with just one person. Pretty helpful slide. I just collected all the links of everything I talked about. So there is a datasets, the Python tools, how to do the processing, and really it doesn't require geographical background, just a very basic image processing to start using the satellite data. And the second thing is the QGIS is an open source tool how to preview the satellite images and to see them collected nicely, because sometimes when you just open these pictures, it looks pretty strange. So O'Reilly recommended to add a slide about rating the presentation. Just to keep in mind, probably everyone has it already. And this is I wanted to talk about the satellite data for today, and I'll be happy to address any questions. Thank you. Yeah. Will the slides be available? Yes, sure. After this session, I'll upload a PDF of the slides. Yeah. Yeah. The question is, do we create different pipelines for the data? Do we have any intercommunication between the sections of processing? Like generally, our pipeline was not that large, and the team was just about 5 developers, and they, uh, like honestly, we didn't do it. But again, it's AWS. It's a pretty straightforward way to do it. We just didn't have our need for that. Yeah. Thank you.